Hi everyone, welcome back to the Microsoft in 29 days series self-paced course. So in case if you have not registered yourself for the course, so you can find the course link in the description of this video. Apart from this, I would like to say that this video is pretty important in regards to the greedy problems because we'll be discussing two greedy problems that are very important. The first one is jump game. It's a pretty standard problem, but the second problem is police and thieves. So in that problem you will learn a lot. So that is a two-pointer approach, so make sure to stay till the end. Now let us discuss this problem, jump game. So in this problem we have been given a positive integer n and we have been given a list of n elements. So each element in the array denotes the maximum length of jump that you can cover from that index, and you have to find out if you can reach the last index of the array or not. Okay, so let us take the sample example and see. So if you have been given this example that is there, so we can say that if we have been given 1 2, then we have been given 0, then 3, then 0 and then 0. So if we start from this index, so this index indicates that we can take a jump of 1 only. So we'll take a jump of 1 when we reach to this index. So in this index either we can take a jump of 1 or 2. If we take a jump of 1, in that case we will not be able to take any further jumps because the number of jumps here is 0 at this index. So we'll say that okay, we'll not take a jump of 1, we'll take a jump of 2. When we take a jump of 2, then what happens, we reach to this index. Now in this index if we take this jump, so we reach this index, and this is not the last index of the array and we cannot take any further jumps, so we'll not take this jump. And what we'll do is we'll take jump like this. Now when we take this jump, so we are able to reach the last index of the array, and that is when we'll say that we'll return a true because we are able to reach the last index of the array as it has been mentioned, because it is said that you have to find out if you can make it to the last index if you start at the first index of the list, right? So when can we not make it? So let us say that we have been given 1, then 0 and then 2. So what we can do here is we can say that suppose we start from this index 1. So what we'll do is we'll jump, and when we make a jump of 1, so we reach to this index 0. Now we reach this index which has value 0. Now from this index we cannot make any jump, so in that case we will return false, whereas for the earlier case we were returning a true. So that is what we have to do. Now when you see this, so we can easily understand that suppose I am currently standing at a particular index I. Okay, so that index has a value array of I. So what are the jumps that I can make from that index? Either I can make a jump of I plus 1, or I can make a jump of I plus 2, up till where I can make a jump of I till I plus array of I. Okay, so that is what we can do. Now we can try to make all these types of jumps and we can see that whether we are able to reach the last index of the array or not. When we apply this approach, so this is nothing but recursion, where we have to repetitively check that whether we are able to reach or not. So let us quickly try and write the code. So what we'll be doing is we'll be given this function in which we'll be given the array and we'll be given n. So we can say that we will return a recursive function, like we'll call a recursive function which will start from the index 0 because the array is 0 based indexed, and we'll pass the array a and we'll pass n. Okay, after we have passed these values, so what we'll be doing is we'll be passing int, we'll be calling this recursive function with the index as I, and we'll be passing the array int a, and we'll be passing the value n. Okay, and then what we will do is we will say that when we'll return a true, so we'll return a true if I is equal to n minus 1. So if I reach the last index, in that case we simply return a true, indicating that okay, this is possible. Otherwise we'll return a false, otherwise we will return a 0, you can say. Now what we will do is we will try and see like what are the jumps that we can make. So we will say that for int k starts from from where will I start making the jumps. So I'll start making the jumps from I plus 1 until where I can make the jumps. So I can make the jumps till nothing but I plus array of I, correct? Till this index I can make the jump, and then we do a k plus plus. After this we'll call the recursive function. So recursive function for this jump k, like at this index k I'll go, and I'll pass the array as well, and we'll pass the n. Now this recursive function will return us a true or a false. So if this recursive function returns us a true, in that case we will also simply return true, indicating that it is possible to reach the last index of the array. Otherwise, if we have iterated for this I and we were not able to reach, so we'll simply return a false, indicating that we cannot reach. Let us try and compile this code to see if it works on the samples. Okay, so we are getting a compilation error. So it is saying, yeah, array, I should name it as capital A. Now let us try and compile it. Seems to work on the samples. Let us try and submit it as well. So I think we are able to pass all the test cases in this problem. But the problem is that this is a recursive approach, and we can further optimize it by using the concept of memoization. So we can say that if a particular state I is already calculated, in that case we will not calculate it again. So we'll say that here we can see that the n value will be maximum 10 to the power 5. So 1 0 0 0 and then 5. That will be the size of the DP 1 2 3 4, like 1 2 3 4 and 5. Okay. Then we'll initialize the DP as -1 memset. Like in C++ we can use this function -1 comma size of DP. So we'll initialize it as -1, and we'll say that if it happens that the DP of I is not equal to -1, if it is not calculated already, then what we do is, if it is already calculated, right? So if it's not equal to -1, then we directly return its value. Okay. Otherwise, what we'll do is we'll calculate its value and then store it and then return it. Okay, that is what we are trying to do. In that case, the complexity of this code is now order of n square. Let us try and compile this now. It seems to work on the samples. Let us try and submit this. But we can further optimize this code from order of n square to order of n, because if we are iterating for every index I, we are iterating for the loop, so that takes order of n square time, and we can further optimize this problem to order of n. Let's see how. So let us say, like, by using the concept of the maximum reachable index. So what we can do here is, let's say we have been given this array, like we have been given, let's copy this again. So if we have been given this array, okay, so if we have been given 1, then 2, then 0, then 3, and then 0 0. So what we can do is we can keep a track of the maximum reachable index for us. So you can see that initially we'll mark mx as array of 0, that is nothing but 1. Okay, we'll keep mx this. Okay, then we'll start from this index. So from this index, what is the maximum reachable index, right? So we'll store that. So let us say this is 1, like this is 2, this is 3, this is 4, this is 5. So I want to reach, like I want to see whether I can reach n-1 or not. Okay, so that is only possible when I can take a jump, like if I can go beyond it, then also it's possible. If I can go till that n-1, then also it's possible. Otherwise it's not possible if I fall behind it. So what we'll say is, we'll say that, okay, at this index, what is the maximum reachable index? So it will be nothing but, like, we can say, simply say that we will iterate for each I afterwards, and I can say that I starts from 1, I is going to be lesser than n, then we do an I plus plus, and what we can identify here is that we can identify that mx, the maximum reachable index, is equal to nothing but max of mx comma array of I plus I. That is the maximum from this index I, that is what I can reach. Because if I'm standing at this index 2, then the maximum that I can reach is this index, right? So that is what I'm storing, because 1 plus 2 is what? 3. So maximum gets updated to 3. Okay, then what happens? Then you will observe that if I see this index, so at this particular index I'm not able to reach it. Okay, at this particular index, if I observe, so if I am here, so I will not be able to reach any further, but still my maximum is 3. And can I actually reach this index 2? Yes, because if I can make a jump from here till here, so that means this is also reachable, so that's fine. Now when I come to this index, okay, so I will say that 3 plus 3 is nothing but 6. Okay, so in that case what happens, like my maximum up till now is 3, and now I can see that array of I is 3 and index is also 3, considering a zero based indexing. So in that case, the maximum jump, like maximum reachable index, now becomes 6. At this index I can say that I can reach till 6. So now my maximum gets updated to what? Maximum gets updated to nothing but 6. Now since my maximum gets updated to 6, so I can say that if, like, I want to reach 5, so if I can reach greater equal to n minus 1, right? I want to reach 5. So if I can reach greater than 5, because you can see I can take a jump here, I can take a jump here, or I can take a jump beyond. So if I can reach, if my maximum jump that I can take, if the maximum reachable index is greater equal to n minus 1, if it is equal to n minus 1, or if it is greater than n minus 1, in that case I will say that simply we can return a true, otherwise we will return a false. But there is a catch in this problem. So for that we have to look at the sample, second sample. So let us say that sample has been given like 1, 0 and then 2. In this case, if we try and observe, so what will happen? So initially we'll keep the mx as 1 and we'll start from this index. Okay, now if I start at this index, so what happens? If we start from this particular index, so we can say that we'll start from this index. Now this index is what, like it's 1, right? Now 1 plus 1 is just 1. So what will happen? Can I reach this index from here? No, I cannot reach this too. So we need to add one more extract condition, and that condition is that, like, we initially initialize mx to a of 0. Then what we can say is we'll we'll run I starts from 0, like I starts from 1, I is lesser than n. Then we'll do an I plus plus here, and what we will say here is basically that mx, if it happens, like I need to say that whether I can reach that index or not, because in this case if you observe here, so I was able to reach this 0, right? I was able to reach this 3 because I could take a jump. So I need to see that if the I that I am currently wanting to cover, right? Suppose I come here, suppose I come at this index, then in that case, like, can I come actually to this index? No, because like if my I that I am choosing, right, if the current I that is there, if I is lesser equal to mx, if the mx is greater equal to the I, then only I can update my maximum. So mx is equal to nothing but maximum of mx comma I plus array of I. That is what we can do here. Okay, so let us try and write the code for this approach, that is linear in order and no extra space is taken. So what we'll do here is we'll say that initially the mx is equal to array of 0, and then we'll iterate. So what we'll say is that for int I starts from 1, I is lesser than n, then I plus plus, and we can say that if I is lesser equal to mx, then what we can say is we can update our mx. So otherwise we'll not update. So mx is equal to nothing but maximum of mx comma I plus array a of I. Okay, that is what we'll do, and in the end we'll check if it happens that the mx is greater equal to n minus 1. So in that case we will return a true, otherwise we'll return a false, that we cannot reach that index. Because if I can reach that index or beyond, then that's fine, otherwise we can simply return a false for this case. Let us try and compile this code. Okay, wait, it's giving a compilation error. So n minus 1, yeah, I should declare it as capital. It works on the samples. Let us try and see if it works on the other test cases as well. So you can see that our solution was able to pass all the test cases. Talking about the time complexity of this code, so the time complexity will be nothing but order of n, and since we have not taken any extra space, so the space complexity will be nothing but order of 1. Thank you. In this video we will discuss the problem police and thieves. The problem says we have been given an array which is of n size, and each element contains either p or t. So every element or every index of the array contains either the character p or the character t, where p indicates the policeman and t indicates the thief. So what we have to do is we have to find the maximum number of thieves that can be caught by the police, and we have to consider these two conditions. So the condition 1 is that each policeman can catch exactly one thief. Okay, so every policeman can catch exactly one thief, so no policeman can catch more than one thief, and a policeman cannot catch a thief who is more than k units away from him. So let us discuss this case first of all and see what we can get. So if we have been given the sample input as p, then we have been given t, then p, then p, and then t. So we can see here k is equal to 1. So a policeman can, let us suppose that a policeman is standing at the index I. So we can understand that a policeman can go maximum till I plus k and I minus k, that is in the left direction and the right direction. Maximum the policeman can go till the k. Now, in the similar fashion, if we see here, so we can say that this policeman can catch this thief and this policeman can catch this thief. So we can say that the total number of thieves that we have caught is nothing but 2. Another thing that could have happened is that this policeman could have caught this thief. Let us discuss the next test case as well. So in the next test case, if we have a look at it, so the next test case says that we have been given T, then we have been given T, then we have been given P, P, T and P. So now in this case we have been given K is equal to 2. So they can be various scenarios, but here what we can do is we can say that this policeman, let's say this policeman catches this thief, okay, then this policeman cannot catch this thief. You can see, like if you will observe here, so let us say that this policeman catches this thief. Now in this case this policeman is left. Can it catch this thief? Because it can move 1 here, then 2 here, so 2 steps, but the policeman cannot go more than 2 steps, so that is why I will be at a loss. So one thing that is very much necessary that we have understood from this case is that this policeman cannot catch this thief. So what we need to observe is that a policeman should not catch this thief. This policeman, the first policeman, should not catch this thief. The reason for that is because in that case this policeman has to cover a distance of 3, which is exactly not possible here, because this is distance 1, distance 2, distance 3. So what we can observe in this case is that if the policeman is there, so the policeman should try and catch the maximum possible thief from it. Why? Because if this policeman is there, so this policeman can go maximum till 2 distance in the left side or the right side. So this policeman, if let's say covers this thief, so in that case he covers a distance of 2, and which every policeman can do. Now what will happen? Now this policeman can easily catch this thief, because he will also catch the thief that is at a distance of k distance, that is at a distance of k away from the left side or the right side. So a policeman will try to first of all see that whether he can catch a thief at a distance of k in the left side or at a distance of k in the right side, and then if a thief is not present at that position, then maybe at k minus 1 in the left side, k minus 1 in the right side. Okay, in this way we can count the maximum number of thieves, and you can see that this policeman can catch this thief. So the total number of count of thieves that we can catch is nothing but 3. So what we can do here is we can have a brute force approach, and since in this case we have been given n thieves, we have been given like the array size is n and we have been given the value k, so k is nothing but the distance. So we can try and check for each and every policeman. We can like for each index at which we can find policeman, we can try to go in the direction k towards the left and k towards the right, but this will be a brute force approach, and our brute force approach could take order of n into k time, which is a lot, and we can try to optimize this as well. How? So we can, for this what we can understand is we have to see this case. So let us copy this case again and try and observe something. So if we carefully observe this case, so what will happen, like t is there, then p, and then t, then p. So what we can do is we can mark them as with the indexes. So index 0, index 1, index 2, index 3, index 4, index 5. Now in this case we can try and apply the 2-pointer concept. Why? Because what we can do is we can first of all put the first like we can make 2 arrays. So let's say first array I am making it as t, which is indicating thieves. So in that array I'll store all the indexes of the thieves. So I'll store 0, 1 and 4, and then in the second array what I would do is I would store the policemen at their indexes. So first of all I'll store 2, then I'll store 3, then I'll store 5, and I'll apply the 2-pointer concept now, because I can see, like I will start 1 pointer I at here, okay, and 1 pointer j in the policeman array. And what I can say is, if it happens, like here the k value is what? Here the k value is nothing but 2. So what I will try to do is I will try to see that if the absolute distance of t of I minus the p of j, if the absolute distance between the index of the policeman and the thief is less or equal to k, then I will count it in my answer and I'll move both the indexes by 1. So I plus plus and j plus plus. So basically I'll do answer plus plus or count plus plus, then I'll do I plus plus, and also I'll do j plus plus. So if I see here, so 0 and 2 have an absolute difference of nothing but less or equal to 2, that is 2. So I will consider it, I'll mark my count as 1 and I'll move to the next index. So my I moves to this index and my j moves to this index. Okay, now what will happen? Up till now my count is 1. Then I can see for 1 and 3 also the same thing applies, because at these indexes also the absolute difference is less or equal to k. So the police can catch the thief. Now I moves to this and let's say j moves to this. So now what happens? I can easily observe that the absolute distance is 1 and which is less or equal to 2. So this will also be counted. So the count first of all changed from 1 to 2, then from 2 to 3. So now the count is 3. So this is how we'll apply the two-pointer approach. But this test case does not expose us to the moving part, like when the distance, absolute distance, is not less equal to k. So let us try and suppose about that instance. So let us suppose that we have a particular index, like let's say the police is standing at suppose some index I, and the thief is standing at suppose, like thief is there, like we are standing at the index of police and we are standing at the index of thief, and they are not at a distance of k from each other. If they are at a distance of more than k, so what we need to do is, suppose if I have the police and police is standing at an index which is greater than that of the thief, so in that case what I need to do is I need to do a j plus plus. Why? Because I need to, if the police is not able to catch the thief at the jth index, then in that case at this index j, so in that case I need to increment my j, because I want the thief to come closer than me, and if I increase j, then chances are that I might get a thief that is closer than me. And similarly, if I have p of I lesser than t of j, so in that case what we can observe is, in that case we can easily observe that if the policeman is behind, if the policeman is behind and the thief is at a distance more than k, so if in that case the policeman is behind, so I need to do I plus plus such that I can get a policeman which comes closer to this policeman at t of j. Okay, so that is going to be the approach of the two pointers. And talking about the time complexity of the two pointer approach, so since it will be a two pointer approach, so the time complexity will reduce from order of n into k to order of n, and the space complexity would be order of n as well. Let us try and write the code for it. So what we will be doing is, we'll be having two arrays. So first of all, like we can make vectors here. So we can say that vector int, like let's say t for thief, and like I will name them, so thief, and I'll have the array for police as well. And then what we can do is, we can simply say that we'll iterate through the array. So for int, like since we are storing the characters, so we can mark it like we will be storing the indexes, so we can mark it as int. Then what we'll do is, we'll say that int I starts from 0, I is lesser than the size, and I plus plus is what we'll be doing. And here what we will observe is, we'll say that if it happens that array of I, if the ith character is equal to thief, so in that case what we will do is, we'll say that we'll store it, that index in the thief. So thief dot push back nothing but the index, so I. Else if that index belongs to the police, so if at that index the police is present, so I'll do what, I'll say that police dot push back index, right, at that index I'll store. And then I'll have my two pointers, so I starts from 0 and j starts from 0, both of them will be starting from the starting of the both the arrays. And then I will iterate until I reach both the ends. So I'll have a count as well, so I'll say that int count is initialized to 0. And then what we will do is, we'll say that while I is lesser than the size of the like if I is indicating the thieves, so while like let's say I is lesser than thief dot size, and j is lesser than the police dot size. So j in the j variable will be iterating through the j pointer will be iterating through the police array, and I pointer will be iterating through the thief array here. So if it happens that, like I'll first of all calculate the distance. So let's say I calculate the distance as nothing but absolute of, distance is equal to nothing but absolute of thief of I minus police of J. So I'll calculate it, and if this distance that I've calculated, if this distance between the police and the thief is less or equal to k, in that case I'll first of all I'll count it. So I'll do a count plus plus here. Then what I'll do is I'll do I plus plus because I'll move to the next index, and I'll do a j plus plus as well. Okay, and else if it happens that my let's say my thief of I is greater than the police of J, right? So if my thief is standing at a like if my thief is greater, right? If my thief is if my police and thief are standing more than k distance away and the police is behind, then I'll try to check for the next police. So I'll do a j plus plus such that I can get closer to the thief, such that my absolute distance can be less or equal to k. And else if it happens that the police is ahead, then in that case I'll do I plus plus because I want a closer thief to me. And then I can say that what we will do is we'll simply return the count part. Let us try and compile this code. Seems to work on the samples. Let us try and submit this as well. So you can see that our solution was able to pass all the test cases. Now talking about the practice problems. So the first problem is stock buying and selling. So in this what we have to do is we have to basically maximize the profit, and this is a very standard problem. Now the second problem is job sequencing. It is also asked very frequently in various interviews, and this problem can be done using the greedy approach. Now the third problem is minimize the height. So in this problem also we'll be given an array of heights and n towers and a positive integer k, and we have to modify the height of each tower either by increasing or them by k or decreasing them by k only once, and after modifying the height should be non-negative integer. So we have to find the minimum number of possible difference of the height of the shortest and the longest tower after the modification that we have done. So these are the problems. Thank you.